All right, everyone. So this lecture is going to be all about junctions, how to form them, what they do, and some of the math behind it. Junctions are extremely important in semiconductor photoelectrochemistry. So this is going to be a pretty important lecture that maybe we'll reference a couple of times. So we talked last time a little bit about the basics of a junction, how it's formed, sort of conceptualizing what's going on. So essentially what happens is that a semiconductor is in electrical contact with some other medium that has a chemical potential different from its own. And then due to this difference in chemical potential, we get charge transfer across the interface, and then we get these electric fields, which cause this junction thing. For photoelectrochemistry, we're mostly interested in semiconductor liquid junctions because you can only do electrochemistry really in liquids. Not strictly true, but mostly you can only do it in liquid form or in solution. Semiconductor metal contacts are extremely important, and we'll have a little side note on those, and that'll help with understanding why certain things happen the way that they do. But for this class, we're mostly interested in the semiconductor liquid junction. So first, let's form a semiconductor liquid junction. So the way that you form one is by taking a semiconductor that you have an electrical contact to and a solution that has some sort of redox couple in it, some sort of chemical species that can undergo an electric change. And then you're just going to drop it in. That's it. That's the whole ball game. You just take your, I'll use a different color. Yeah, let's use yellow. You just take your semiconducting species and just drop it in the water. That's it. That's all you got to do. So pretty easy. So let's imagine that our semiconductor is doped. Because if we do it with an intrinsic semiconductor, things get a little bit weird. Plus, if we're doing photoelectrochemistry, if it's an intrinsic semiconductor, its conductivity is probably crap. So we don't want to deal with that. We want something with decent conductivity, something that will actually do some chemistry for us. And plus, some of the concepts don't make a ton of sense in intrinsics. So we're going to work with doped. Arbitrarily, I'm going to say that it's N-type. So all of the stuff that I'm going to be discussing is going to be specific to N-type semiconductors. P-type semiconductors, like most of the time, work pretty much the same, just in reverse. So I'll have a little note on the end as to like what things look like if you're doing a P-type semiconductor, but in the generalities are the same. Okay, so at T equals 0, so nothing has equilibrated yet. I just dunked the semiconductor into our solution. Nothing has equilibrated. So our junction looks like this. We have our energy of our conduction band, Fermi level, valence band, and the energy of our redox species. Now note the energy of our redox species is below that of our Fermi level, which means that it has a lower chemical potential, which means that we are going to cause electrons to flow from here to here, right? There's going to be an abundance of electrons on the semiconductor side of our junction. Charges are going to flow into the solution. Now, where are those charges coming from? Right, in the last lecture, we talked about that they're coming from some of these little atoms in the lattice. But since we're working with a doped semiconductor, those charges are mostly coming from the dopants, right? Because if we have a doped semiconductor in the extrinsic region, so we have N over ND, temperature, so we're going to do this number. So we're working in this region here, right? If we're taking electrons from our semiconductor, well, basically all of the electrons in this region are from our dopants, right? So that's what's going on here. We're taking electrons primarily from our dopants because they're easy to ionize, and that's where most of these delocalized electrons are coming from at this potential anyway. All right. So remember that at room temperature, basically all of these dopants are ionized, but the semiconductor remains neutral because those electrons that we have now donated into our conduction band are just sort of delocalized. They're floating around. So while the dopants are formally ionized, the whole semiconductor is neutral. But now, since we are going to be taking electrons from the system, our dopants are more formally going to be ionized. So we're going to have excess positive charges on the semiconductor side of our junction. and equivalently excess negative charges on the right side of our junction, on the liquid side. So this causes a charge buildup. And interestingly, because these dopants are so easy to ionize, essentially all of the dopants within a certain distance that we're going to call W from the interface are going to get ionized. So if you are within this distance W that is needed to balance out some charges, and we'll get to exactly why that happens, but within this distance W, all of the dopants are ionized, all of them. So you could, so that'll be a useful concept later. We are going to call that region of the semiconductor where all the dopants are ionized, it has been depleted of its electrons. We're going to call it the depletion width. So W is our depletion width. And that is the region in which all of our dopants are ionized. We have been depleted of electrons. There are not that many electrons hanging around in this region in the semiconductor. The only thing we have left are ionized dopants. By the way, likewise for p-types, these are going to be excess negative charges and then positive charges on the side of the interface. The depletion width is also sometimes called like the space charge region. So if you run across that, that's all that means. But the depletion width is the more generally used term. So let's see what's going on here physically, like using physics, by taking a test charge, and we're just going to drop it way over in the bulk of the semiconductor, so far away from the junction. And we're just going to move it closer and closer and closer to our junction and see what happens, see what it feels. So we're going to just plop this negative test charge way in the bulk, which means way far away from the junction. All right, so when you're this far away from the junction, the negative charges in the solution, so the ones that are way over here, are going to be screened by the positive charges in the depletion width. So these guys over here. So essentially, that electron experiences no electric field, more or less. And one way to envision why this is happening is you can think about, let's say we have 2 point charges. We have a positive and a negative, right? So our electric field lines are going to look something like this. They're going to be nice and parallel in here. And then these are going to sort of bend, and these are going to sort of bend. Sort of like this, right? So if you imagine putting our test charge like way over here, it's not really going to feel any of this, right? That's all very close to where these charges are. If you're far enough away, the electric field that you feel is essentially nothing. So we call that the quasi-neutral region, because the charges in that region, far away from the junction, are not experiencing any electric fields. They act as though the semiconductor is completely neutral. They can move around freely. There's no forces affecting their motion. It's called quasi-neutral because the semiconductor at this point is charged. So it's not strictly neutral. And you might notice that the potential energy, the absolute potential energy of these electrons has changed because the band has bent. But the electron doesn't really notice that. All it knows is that there's this potential energy field that it can move around freely. There's no barriers to its motion. Okay, now let's take our point charge, and we are going to now move it closer to our junction. Once we hit the depletion width, W, all of a sudden things change very quickly. Remember, in that width, basically everything is ionized, which means that the charge density increases very rapidly. So you can approximate it that outside of W, nothing is ionized. And inside of W, everything is ionized. So the charge density is almost a step function. Now, of course, we're working with real systems, so it's not perfect. There's this little bit of tailing right here. But if you can approximate this as a step function, that there's nothing, and then there's just charges in here. So all of a sudden, our test charge is going to feel the effects of having a whole bunch of other charges around it very, very quickly. Also, just a note on some of these graphs that I'm going to be drawing. There's similar balancing effects on the other side of this interface. So this is the liquid over here. And so if you were to look at the charge density here, it's going to be like a super, super thin, like a vanishingly small charge density here that just goes up, and that has an area equivalent to this. But because it's so vanishingly small, it doesn't really affect things. And so I'm going to pretend it doesn't exist. Just know that it does exist and it's over there, but we're only going to talk about the semiconductor side. Okay, so now we hit the depletion width. All the dopants are ionized, and there's uniform charge density, Q and D in the region. Now remember, N sub D is going to be the number of our dopants, and we're just multiplying that by the fundamental charge, saying each dopant has one fundamental charge. So the total charge density is going to be equal to that many charges, right? Cool. Now, the electric field experienced by our charge at any point in our depletion width is going to be equal to this equation here. The electric field is going to be equal to the fundamental charge times the number of dopants, so our charge density, divided by this epsilon s, which is just our static dielectric constant, multiplied by the distance x. And we are going to say that this is within this region that we're going to call W. And note that we're saying that 0 is here and W is here, right? So inside this region, the electric field is given by this equation. And let's just play around with this equation for a second. So let's see what happens if we increase our distance, right? So we're going to get closer to the junction, okay? As we get closer to the junction, so if X increases, E also increases. It increases linearly. Likewise, what if we can't change that. We can't change the fundamental charge constant, but what if we increased the number of dopants? If we increase the number of dopants, the the electric field strength is going to go up, right? If we assume that we are just increasing the number of dopants, we're just increasing the amount of stuff that gets ionized, which means that there's a higher electric field. What about if we increase the static dielectric constant? In this case, if we increase the dielectric constant, which is like sort of the ability of an electric field to permeate a material, the electric field goes down. So if the static dielectric constant is higher, the electric field is lower, just because it's a little bit more difficult for that electric field to permeate the material. All right. So therefore, the electric field increases as we get closer to the interface. And if we take it to its logical conclusion, the maximum electric field that we reach is going to be equal to this equation here, when X equals W, right? So we can define a maximum electric field strength, E max, equal to Q N D over epsilon S times W. And remember, this is repelling our test charge. So as our charge is trying to go through this region, it's having a hard time. And not only is it having a hard time, because the electric field strength is going up as we get closer to the interface, it's getting more and more difficult for the electron to move towards the interface as it keeps going. The positive charges from our ionized dopants are going to keep pulling it back harder and harder and harder. All right. So as our electric field increases, so does our electric potential. So as I'm saying that this electron keeps getting pulled back harder and harder and harder. Well, how much? What's its potential energy? How is its potential energy changing? Because remember, we started out with this flat band, so the electron could move around freely. It had no idea that there were any electric fields anywhere. It could move wherever it wanted. But now its potential energy is changing. The potential energy landscape is changing. There's a hill for it to go up. In fact, one of the most useful concepts that I've found is this sort of saying, electrons sink, holes float. So if you look at a potential energy diagram, and let's just say the potential energy goes like this. So this is, we'll just call this an arbitrary U, some potential energy. Electrons want to sink down this way, right? So if there's a potential energy that's bending up, the electron is going to have a hard time going that way. But if the potential energy is bending down, the electron is going to go that way rather easily. It's going to prefer to go that way. But holes, remember, are the absence of an electron, so they move the opposite way. So a hole floats. So a hole actually wants to go up this way. If there's a barrier like this for a hole, that's actually favorable. It wants to follow that path. But if you have a hole over here, it actually doesn't want to go this way. It would prefer to go back up the potential energy diagram. Cool? That'll just help remember where things are supposed to go. Electrons sink, holes float. So let's see how our potential energy landscape changes. So it's going to increase with the square of distance. So our potential energy, our electric potential energy, or our voltage, is going to be equal to negative. This is just making sure that we're using the right sign for our electrons and holes. The fundamental charge times the number of dopants. So our charge density again, now times 2, or divided by 2 times our dielectric constant, multiplied by your distance x squared, again, within your depletion width. So what that looks like graphically is that as our electron tries to move closer and closer to W, the electric potential, or the potential barrier to that motion increases exponentially. Increases exponentially, just like that. And again, just like our electric field strength, we can define a maximum voltage. We can define a maximum electric potential at x equals W. And that potential is this here. So it's going to be defined as Vmax. We're going to take the absolute value so we don't have to worry about this minus sign here. And its magnitude is going to be equal to our charge density divided by our 2 times our dielectric constant multiplied by the depletion width squared. All right. This is also called the built-in voltage. It's equivalent to the chemical potential difference between our semiconductor and our redox species, right? So if you were to measure, if you were to like separate these, so now we're going to pull our semiconductor out of the solution, rinse it off so it's nice and clean. And we're going to put one end of a voltmeter on our semiconductor, and we're going to put the other end of a voltmeter into our solution. The potential difference that you would measure between those two is your built-in voltage. So likewise, you could look at it in your potential diagram. So here, none of our bands are bent. Let me, here. So this is our semiconductor, this is our metal. And the potential difference is going to be between the chemical potential of our semiconductor and the chemical potential of our metal, or of our solution. And thus, it's the difference between their Fermi levels. This right here, this is VBI. Now, this is interesting because in order for us to get to equilibrium, remember, we have to balance out our potentials. We have to balance out our Fermi levels. They must be equivalent throughout the material in at equilibrium. So that's sort of how we get to how wide W needs to be, right? It needs to be exactly wide enough to build up enough potential energy to cancel out VBI. Thus, we can solve for how wide it needs to be. So we can take our expression for the built-in voltage, and we just solve for W. And we get this expression here, that the depletion width is going to be equal to the square root of 2 times our dielectric constant times our built-in voltage, which again is pretty easy to measure, divide by our charge density. Okay? So you can also think of it as the difference between the neutral and charged semiconductor band locations. So when we draw these things, right, you'll notice that like this is where the EC starts out. I draw it like this, where EC comes down. And this difference here is VBI, right? So it's a pretty important parameter. And you might have noticed that with our terminology, that is the built-in voltage of our system, that it'll be pretty important for constructing devices later on. And it's a good consideration for figuring out like, well, what materials do I put where? What would their built-in voltage be? Do I want a high voltage, a low voltage, that sort of thing. So while the conduction band and the valence band do bend, and they do change their locations, the difference between the bulk, like the bulk difference between the conduction band energy and the Fermi level doesn't change. We call that Vn. It's technically QVn, so that's something that I'm going to do a lot here. Recall that I'm looking at E here, these are energies. So like ECB is the conduction band energy. That's equivalent to the fundamental charge times the voltage of the conduction band, right? All right, because this is in electron volts. So this is like electron times volts, right? Because this is the charge of an electron. So just make sure you're careful with that, that if you're, you don't want to mix potentials and energies. They're not the same thing. You have to add that factor there. All right. So that difference between the equilibrated, between the ECB, like our conduction band, and our Fermi level at equilibrium is V of n, and it doesn't change in the bulk of the semiconductor, right? So essentially what we're saying is the difference between the chemical potential and the conduction band in the bulk semiconductor, in the semiconductor that is not affected by any electric fields, remember, we're in that quasi-neutral region, that potential difference is always the same. However, it is not necessarily the same inside the depletion width, right? Because now we have these charges and these electric potentials that are going to cause differences between where our conduction band is and where our Fermi level is. All right, so the difference between the equilibrated Fermi level and the conduction band at the interface, so this is now our V of n, or V sub n plus whatever our VBI is, right? So now we're saying the maximum voltage that we can build up at our interface, plus the potential difference between where we between the Fermi level and the bulk semiconductor, is going to be called the barrier height. So if you look at a band bending diagram, the difference between where this conduction band started and where it ended is our built-in voltage. The difference between where our conduction band and our Fermi level are at equilibrium, or in the bulk, is our V sub n. Our barrier height is both of those added together. So what you can think of that is like how much, like what's the barrier for an electron to go from our chemical potential all the way up here, right? Which will be important because if we're doing chemistry, all of our electrons are going to be hanging out at around this level. So we want to know how easy it is to go say, back and forth between our semiconductor and our interface. So I've been drawing the conduction bands, like I've been drawing the band bending such that it's like as if this location here, this conduction band energy at the interface is pinned. It's not moving, it's stuck. And then we pull it down in response to our electric fields. But this sort of begs a question. Why do they bend like that? So, because I showed you that the voltage, right? The voltage goes up, or like the chemical potential, the electric potential, excuse me, the electric potential goes up like that exponentially. So why don't the bands bend like that? Why don't we have the conduction band at its neutral level, and then as we get closer to the interface, we just bend it up, right? Why does that happen? All right. So the answer is sort of in this concept of a work function, electron affinity, and vacuum level. So this is more applicable to semiconductor metal interfaces, but the same concepts apply here. It's just easier to understand if you link a semiconductor and a metal. So I'm going to use these diagrams to explain what's going on. So just like if we have a semiconductor and a liquid, we have some Fermi level for our metal over here, some Fermi level for our semiconductor, we have our conduction band. We also have this thing called the vacuum level. So the vacuum level is the energy at which you can liberate an electron and it'll just go into free space, into the vacuum. So we have this thing called a work function for the metal, which if you've ever done, say, like X-ray photoelectron spectroscopy, things like that, you might have heard of work function before. You can think of it as like how tightly your metal holds on to its electrons. So in order to pull an electron off of this metal, I need to overcome this work function here. I need to input enough energy. Actually, this should be Q. I need to put up in enough energy to overcome this barrier. Likewise, for a semiconductor, in order to liberate an electron from any given point, any given location in the semiconductor, I need to input the semiconductor's work function. I need to put in whatever that barrier is. There's also this other quantity called the electron affinity, or chi of A. So that for the electron is like chemically, how electronegative is it? How much does that atom or this material want to hold on to electrons or accept electrons? So this is linked to its chemistry. Okay, so let's see what happens when we put them together, because here they're separated. When we put them together, something interesting happens. So there are two rules for a junction. One, the Fermi levels must equilibrate. So the Fermi level throughout a material, throughout a junction, must be uniform, has to be a flat line. Rule number two is that the vacuum level must be continuous. So the vacuum level is never going to have just like a jump in its energy. It's going to be a continuous line. So let's look at what happens when we put these together. The electron affinity of our semiconductor does not change if we make it charged. That atom, its fundamental chemistry is still there, right? It should still be just as easy for it to hold on to, or it still wants to hold on to certain electrons a certain amount. It still wants to accept electrons a certain amount, just by its fundamental chemical nature in its conduction band. However, the amount of energy required to actually pull off the electrons is going to be different inside our depletion width, inside this region here, which remember is charged. So even though, remember, it's the same atom, so like silicon still acts like silicon, it still has the chemistry of a silicon atom. So that's why this chi of A isn't changing. That's just like a part of the material. So you'll notice that the difference between the conduction band and the vacuum level never changes. It's always the same, and they're always parallel to each other. The conduction band and the vacuum level, always. But what does change is the difficulty of removing an electron from the semiconductor. So in the bulk, where there's no electric fields, it's still the same, right? It's the same value, which makes sense. There's no electric fields, should be just as easy to pull everything off. But at the junction where there's charged atoms, it is more difficult to pull off, to liberate one of those electrons from a charged species, because the nuclear charge is less effectively screened. So this could be a little bit confusing, because I sort of said like, it's just like, it wants to hold on to things just as much. But this is a difference between like fundamentally what the atom wants to do and sort of this, its fundamental ability to hold on to things and release things, and what its actual current makeup is. So think of it like the chemistry of a sodium ion is going to be like similar to that of sodium metal. The difference being that it is more difficult to pull an electron off of a sodium ion. So in this region, there's a larger barrier. The work function increases. And in fact, it continues to increase until it reaches the work function of the metal. And in order for that to happen, the only way that this can happen for our vacuum level to be continuous, because remember, it has to go from being the level of the semiconductor to the level of the metal, is that vacuum level needs to bend. And we're not doing anything on the side of the metal, right? That chemistry is like, it's kind of doing nothing there, which means we have to pull this down. All right, so that's why it's doing it. You can sort of think of it like, well, this is now a charged semiconductor, which means if we say like this is the energy going up, you know, which one would an electron rather be in? A positively charged semiconductor or a neutral semiconductor? Like, it would rather be in a positively charged semiconductor, right? It's going to be more stable. Also remember that what we're doing here, clean this up just a little bit. What we're doing as we get closer and closer to the interface, we are pushing the electrons back down, right? So they're going to sort of slide downhill here, back into the bulk. So maybe if that helps with your understanding. Also note, this difference here is VBI. So just like for a semiconductor, if you take the difference between their Fermi levels, you can get your VBI. If you take psi of m, well, I'll do it this way actually. I want to make sure it makes sense. If we, psi of m minus psi s, it's going to be equal to our VBI for a metal. So hopefully that makes a little bit of sense. The reason that the bands bend this way is because we're not changing the fundamental chemistry of our species. And you can also think of this as like, you know, if we add a dopant, now we're changing the chemistry, right? If we, actually, no. Yeah, no, if we're adding a dopant, we don't fundamentally change where the conduction band is, right? The conduction band, which is where those electrons have to be in order to be delocalized, that's going to be in the same spot all the time, energetically, with respect to a vacuum. So the fundamental chemistry of our semiconductor isn't really changing that much. We have the same atom, right, or the same material. But now we've introduced charges at one portion of it, which increases our barrier height, increases our work function, as it were, and continues to increase the work function until we meet that of our of the material on the other side of the interface. It's easier to think of with a metal, works the same for a liquid. This is a really confusing concept, but like these two rules here are why the bands bend this way. All right, cool, cool. All right, So now we know that there's this depletion width, we have these charges build up, we have a potential energy gradient. Cool. So now how do our electron concentrations vary? So we've moved our electron closer and closer and closer to the interface. We said that it's more and more and more difficult for the electron to exist at each of those points. So how many electrons do exist at each of these points? Well, using the Boltzmann equation, we can calculate the number of electrons at any given point in our depletion width. So what we're going to do is relate the number of electrons in the bulk, so our bulk electron concentration, N sub B, to the concentration at any other point, which is going to be N sub X, or N of X. And that is going to be a function of the potential energy. So the Boltzmann equation is going to look like this. So we have the N sub B times the exponential of Q times the potential energy. So remember, this is going to be the energy, actually. So Q times the voltage at any given point divided by KT. And if we take this to its logical conclusion, if we go to a location in the bulk where the V of X in the bulk is equal to 0, well, then N of X is just equal to NB. But in chemistry, the bulk electrons are generally not that important because it's hard to get to them. They're far into our material. The only ones that are really important are the surface electrons. So it's good to have an expression for figuring out how many surface electrons there are. So let's go the other way. Let's say, what is the potential energy at the interface? What's the maximum potential energy? It's VBI, right? So we're going to take our expression here, and we're going to say at the surface, X is equal to W. And we're going to define a new expression for N sub S, which is going to be the number or the concentration of electrons at the surface to be N of W. We're just going to say this is its definition. And then we are going to use the expression that we already know, which is that V of W is equal to actually negative VBI. Remember that V scales inversely with X squared. It's only the, remember, VBI. This is where we get like this maximum, like absolute value, but the voltage actually is inverted. So if we plug this into our expression, we get that the concentration of electrons at the surface is equal to the concentration of the electrons in the bulk multiplied by the exponential of negative potential energy, electric potential energy, which is QVBI, which recall is going to be our Vmax. So our maximum potential energy difference divided by KT. So let's look at what happens as you get closer and closer to the interface. As you get closer to our interface, this part of the expression is going to get larger and larger, which means that this exponential is going to get smaller and smaller. So we expect N sub S is going to be less than N of B. And the degree to which it is less than the bulk electron concentration is going to be based on what your built-in voltage is. So if you have a large built-in voltage, you're going to have a small concentration of electrons at the surface, which makes sense because it's really, really hard for them to exist there. There's a very strong potential energy gradient pulling them back into our semiconductor. All right. Now let's put all of this together. So a semiconductor liquid interface will result in a charge transfer that generates an electric field of a certain width. And that width is big enough to balance out the potential energy difference or the built-in voltage between the semiconductor and our solution. And it results in a barrier to further charge transfer, which is going to be this 5B, which, in case we didn't get to that earlier, is here, right? So this causes this is the result of an electric field that is present inside the semiconductor now. So there is an electric field, not just like in electrochemistry, you might see that there's like this Helmholtz layer. So there's an electric field that's sort of equivalent on both sides, and it's in fact usually mostly in the solution. For our case, we actually get that the electric field is mostly inside the semiconductor, which we saw in that graph of charge density versus distance. Now, this electric field is super useful because it separates charge, right? If we're having an electric field, it's going to push charges one way or another due to drift. Now, recall in our example of how to convert solar energy, we looked at how plants convert solar energy. And one of the things that they do is they need to separate our charges. We need to separate our electron from our hole because if you don't, they just recombine and you get no energy. The plants do this by creating a potential energy gradient that pulls the electron down and down and down and down and further and further and further away. And that sacrifices a good amount of the electron's energy to move it just a micron or so. But we don't need to do that now. Now we have an electric field. And this electric field is typically on the order of like 10 to the 5 volts per centimeter squared, which is pretty big. And the fact that carrier mobilities in the conduction band of a semiconductor are usually pretty good because it's the conduction band. The electrons are sort of free to move around, right? This is where their mobilities are highest. So that allows us to move charges really fast, like 10 to the 7 centimeters per second, which means that you can get fantastic charge separation very quickly. So for our example here, you can get charge separation on the order of a micron, which is pretty good. It's very, very difficult for an electron and a hole to recombine at a distance of a micron in like 10 picoseconds, which is great. And not only that, because the electric field is a result of just what happens when you put your semiconductor in contact with your solution, it stays there. It forms spontaneously and it stays there. So we don't have to worry about continuously putting in energy to keep that field up. It's just there. So that's great. So let's dissect now our band bending diagram. So if you look at a band bending diagram, we find the conduction band, Fermi level, and the valence band, and make sure to always label all this. Now the Fermi level, remember, once we equilibrate, is going to be equivalent across the entire system because it's at an equilibrium. So there is no one part of our system that has more potential, more overall chemical potential than any other, right? But our conduction band has now bent. We say that it's bent up because it goes this way, but remember, we've just pulled it down. A little confusing, I know. So our conduction band and our valence band have both bent because not only is our electron affinity the same at every point, our band gap is also the same at every point. So our conduction band and our valence band bend the same amount. All right, so we have this built-in voltage, which is the difference between our initial Fermi level and our initial redox couple level. It ends up being the difference between our maximum potential energy, where like our maximum potential is, and the bulk potential. We have the difference between the bulk conduction band and the Fermi level, which is V sub n, which is the same in both our original system and our final system. We have our barrier height, which is going to be this phi of B, and which is equivalent to the built-in voltage plus that V of n. And for when we look at metal junctions, we have the work function of our metal. We have the work function of our semiconductor, and they will bleed into each other. And the work function in between here so the work function in this depletion width is going to be equal to work function of the semiconductor plus some potential energy up to when we get psi of W equal to psi of S plus V max, or VBI, which is equal to the metal, or in our case, the chemical potential of our solution. It's kind of weird to think of a solution as having a work function. And all of that electric craziness happens within this region W, this depletion width, the width of which is equivalent to the width of semiconductor you would need at your given dopant concentration to build up enough charges to completely, to build up a large enough electric field to completely cancel out VBI, which is like a lot of and then, but hopefully it makes sense with this diagram. And then of course we have over in this area, our quasi-neutral region, where the electrons don't really know that anything's changed. So that's the basics of a junction. That's how they work. And hopefully at this point, if I give you a band bending diagram, you can identify all of these different pieces. You can identify the built-in voltage. You can identify V sub n. You can find the barrier height. You can find the depletion width. You can find the work functions. You can find the electron affinity. You can find the band gap. And just as a note, if we were doing this for a p-type semiconductor, our bands just bend the opposite way. So in this case, we have EV, E, F, C, and our E, A minus. And now our QVBI is down here, right? Or equivalently up here, makes no difference. And this time, if this was, say, like a metal, so now we have our vacuum level, which is going to increase like this, so that our affinity is always the same. And in this case, remember how we said in that region, in our depletion width, for an N-type, it is now more difficult to pull an electron off because now we have positively charged dopants, dopant ions, in this case donors, right? For a P-type, we have actually decreased the work function, right? Because the original Fermi level was like somewhere down here. And so now it is easier to pull electrons off inside of our depletion width because we built up negative charges. So now we have negatively charged acceptors, which makes sense. You have excess negative charge, it's easy to pull it off. But remember, the electron affinity stays the same because we have the same semiconductor. All right. There is one weird case that we'll consider today, which is what if the Fermi level is, what if we keep with our N-type, but instead of pulling the Fermi level down, what if we need to push it up a little bit? So what if the energy of our species is in between our Fermi level and our conduction band? So in this case, electrons are going to flow the opposite direction than they have. They're going to flow this way, right? So this is called accumulation. So before we're pulling electrons out and we are depleting the semiconductor of its charges. Now we're going to add charges to the semiconductor, which means it's accumulating charge. So this is going to cause an accumulation layer or an accumulation width. And unlike our depletion, which only really affects our dopants, right? Because we're only going to be pulling off stuff from our dopants. The accumulation is going to dump stuff directly into our conduction band, which is going to be spread out over the entire lattice. It includes both your dopants and your intrinsic atoms. That means that the ability of the accumulation layer to support charge is higher. It can hold more charge per unit area. That means that the accumulation layer is generally smaller than a depletion width for the same amount of charge that needs to be dropped. Now, this thinness actually is bad, because if it's so thin, usually on the order of like 100 angstroms, and that is thin enough that you can tunnel. The electrons can tunnel back and forth. So even though the electric field strength can be rather large, one, you're sort of pulling electrons now into your solution, because now remember, electrons sink, holes float. So electrons want to go this way. You also have a very thin electric field, or like a thin layer in which your electric field is present. So it's easy for that electron to tunnel through the barrier. And that means that the charge separation is usually not great. So we tend to not want to use those for solar devices. Okay, so at this point, we've gone through the fundamentals of junctions, focusing mainly on semiconductor liquid junctions. In the next lecture, we are going to look at one odd case, this thing called Fermi level pinning. So we're going to see, we showed that like Fermi level has to change in order to match everything. Well, there's these weird situations where it sort of acts like it doesn't. And then we are also going to look at p-n junctions. We are now going to put one semiconductor in contact with another semiconductor, which is going to cause things to be a little bit different than we've seen so far. So I'll see you in the next lecture.